Chapter 13 is all about chemicals dissolved in solvents, so-called solutions. So, when you're dealing with a chemical, you can determine how much of it you have by weighing it out if it happens to be a pure chemical. Quite often, in a lab setting, your chemical is dissolved in some kind of solvent, typically water in intro chem or gen chem. And when you have that, you have to express just how concentrated the chemical is in the so-called active ingredient. Now, throughout the chapter in the book, they call the active ingredient the stuff you're interested in. They call that the solute. So you have the solute, that's the stuff that's dissolved in the solvent. And when you're handling stuff like that, you're handling a solution. The unit that we use to express concentration is molarity. Molarity is a very big concept in chemistry. Again, it's simply a unit of concentration. It's similar to alcoholic proof. You know, you can have 70 proof vodka, 110 proof vodka. 70 proof is 35% alcohol. The 110 proof, it's more concentrated. It's 55% alcohol. So the proof represents the concentration of the active ingredient, the solute. So in vodka, the solute is alcohol, and it's dissolved in the solvent, which is water. So, one big thing not to get confused about, don't go down this rabbit hole. Some people confuse concentration and amount. Not the same thing. They are not the same thing. Let's say you have one shot of 110 proof vodka. That's the concentrated stuff. That stuff's much more concentrated than the 70 proof. But if you have one shot of it and you have 3 shots of the 70 proof, hey, guess what? The 3 shots of the 70 proof is gonna have more alcohol total. So drinking 3 shots of this, you would end up consuming more alcohol than if you drank 1 shot of the 110 proof. Don't mix up concentration and amount. So the concentration is one thing. The total amount of the chemical present, well, that depends on the volume. So let's get back to molarity. Now, in a typical lab setting, you have chemicals dissolved in water or other solvents. And there you find them in bottles. If you've been taking the lab portion of the course, you've probably seen bottles like this on the shelf, 6.0, that big capital M, and then the chemical's formula or the name, hydrochloric acid. That's the liquid level in the bottle, if you're wondering about my art. So, the way you pronounce that M is molar. So you would say to somebody, hey, can you hand me this bottle of 6 molar hydrochloric acid? So you'd say 6 molar hydrochloric acid. That's how it's pronounced. But it stands for the molarity of the thing. So when you see this 6.0 molar, what does that mean? Molarity is defined this way. Molarity, or the concentration, is moles of the solute, the stuff you're interested in, divided by the liters of the solution. So moles of the active ingredient, the stuff you're talking about, divided by the liters of solution. And here's a big thing to realize with molarity. When you see it like this, when you're handling a bottle that's labeled like this, it's not immediately obvious, but this is a conversion factor, that 6.0 molar. If I were using this chemical, I would rewrite that as 6.0 moles of hydrochloric acid for every 1 liter of this solution. Hey, this is a conversion factor. I got a number with units on the top, another number with different units on the bottom. This allows me to convert liters of the solution into how many moles of the stuff I use. Or if I flip it upside down, I could use this to convert moles into liters. Again, you can always take any conversion factor. You remember, you can take a conversion factor and flip it. So you could write this as 1 liter for every 6.0 moles. But again, the definition of molarity is moles on top, liters on the bottom. So again, don't go down that dark path of confusing molarity and moles. You know, molarity represents a concentration. Moles represents the amount. So let's go ahead and give you a quick example of using molarity, using this molarity here as a conversion factor. Let's say somebody adds 40 milliliters of 6 molar hydrochloric acid to a beaker. Does that mean the beaker contains 6 moles of hydrochloric acid? No, it does not. The 6 molar is the concentration. You add 40 milliliters of the stuff, that's not 6 moles. Well, how much is it? How many moles did we add? Hey, you can do this. 40.0 milliliters. Hopefully you can do this conversion in your head, but if you can't, you can always write out the conversion factor. 1 liter is the same thing as 1,000 milliliters, and you'd see that 40 milliliters is 0.040 liters, right? So if they add 40 milliliters, they've added that many liters. Well, how many moles of hydrochloric? Is it 6 moles? No, it's not. 0.040 liters times 6 moles per 1 liter is going to be 0.24 moles of hydrochloric acid. So if you add 40 milliliters of stuff from this bottle, so 40 milliliters of this concentration, hey, you've added that much. You've added that amount. Again, moles represents the amount. Molarity represents the concentration, not the same thing. Okay, you're going to see 3 types of molarity problems that you have to be familiar with. You already saw the first one, using the molarity as a conversion factor. Another one that you're going to have, actually the first one on our flip page here, is calculating the molarity of a solution. So any problem that says, what is the molarity, or find the molarity, determine the molarity, it's this type of problem. And how do you deal with these? You just remember the definition here, just right there. I'll rewrite it. Molarity is moles divided by liters. So any problem that says determine the molarity, find the molarity, somewhere in that problem it's got to give you enough information to find moles. Somewhere in the problem it's got to describe the volume. You might have to change it into liters. You simply divide the top number by the bottom number. So in our example here it says 8 grams of sodium hydroxide has this molar mass. It's dissolved in water and then it's diluted to a total volume of 750 milliliters. What is the molarity of the sodium hydroxide? Well, the molarity of your sodium hydroxide is going to be the moles of sodium hydroxide divided by the liters of the solution. Hey, 8 grams, and they gave us the molar mass. What's molar mass good for? Converting between grams and moles. So you take your 8.00 grams. You'd say there's 1 mole for every 40.0 grams. And you would come up with how many moles of sodium hydroxide there are. It's going to be, what is that, 0.2. 0.200 moles of sodium hydroxide. So that's telling me this top number here has to be 0.200 moles. Hey, the 750 milliliters. Hopefully you can do this in your head and you can very quickly say 750 milliliters is 0.750 liters. Divide the top by the bottom, and you'd say it's 0.267 molar. So that would be the molarity of the sodium hydroxide there, 0.267. If you couldn't do this one in your head, all we did there was 750 milliliters, 1 liter for every 1,000 milliliters. So all we're doing is scooting this decimal point over 3 times, and it's 0.750 liters. So that's where we got that guy from. Okay, so if they say find the molarity, it means you got to find moles, you've got to find liters, divide one by the other, you've got your molarity. Now, you already saw an example of this using molarity as a conversion factor. So let's see here. The bottle says it's 6 molar hydrochloric acid. Again, what that means is 6 moles of hydrochloric acid for every 1 liter of the solution. How many moles are in 25 milliliters of it? Well, 25 milliliters, if we change that into liters, would be 0.0250 liters. And again, all I'm doing there is using this as my conversion factor, but I'm kind of doing that one in my head. So changing milliliters into liters, all I have to do is scoot the decimal point over 3 times. That's how many liters I have. And again, the 6 molar means, 6 moles for every 1 liter. So I'd say 6 moles of the stuff for every 1 liter. And that would give me 0.15 moles. 0.15 moles of hydrochloric acid. That's supposed to be a C. Hydrochloric acid. There we go. Another example of using that as a conversion factor. Let's say for some reason you happen to need this much hydrochloric acid. Remember, the mole represents an amount. For some reason you need that much hydrochloric acid. How many milliliters of that 6 molar stuff do you need? Start with this number. Here's 0.45 moles of hydrochloric acid. You need a conversion factor here, right? Oh yeah. that guy means this. 6 moles per 1 liter. There. So again, that means this. Well, I want my units to cancel top to bottom. So if I have moles up here, I'll put my 6 moles of hydrochloric acid down here, my 1 liter up there, and you can see how moles of hydrochloric acid gets canceled out. Oh, it's asking us for how many milliliters, so we'd say, oh, there's 1,000 milliliters for every 1 liter. And you can see how liters cancels out. And your answer here is 75.0 milliliters. So if you were cooking away in a lab and you're using stuff from this bottle and you happen to need 0.45 moles of this, you would measure out 75 milliliters of it. Again, molarity, that 6 molar thing, that big old 6 capital M, is simply a conversion factor. We're going to wrap this up in a second video. I'm trying to keep the videos short, so this was the first half of chapter 13.